No. Is it recording now? Oh yeah, it is recording. You're recording. Yeah. Too bad. Forgot to record that. Okay. So the last part is just a few complementary topics. I don't want to say advanced topics. Not necessarily they are not that advanced, but these are some complementary topics on different parts of the PLC. There are 4 points that I want to speak about that. The first one is about a little bit about the operating systems of the PLC. The PLC program that we build the PLC program in this OB1, okay? That we will look at that in a few minutes, but this is the PLC program that we built. But the PLC, the whole PLC CPU, in addition to running this program, it should do some other tasks. It should also run some other tasks to let us to run this program and control the process. This especially is regarding reading from the input and sending the output command to the output devices, whether digital input or digital analog input or digital output or analog output. In fact, if you look at the whole structure of the operating system of the PLC, it's a kind of cycle. So the program runs from the top to the end. Okay, starts from the first rung, let's say from the first rung, from the first network, let's say from the first network or from the first rung in this network, and then one by one they are run, okay, to reach to the end. What will happen at the end? We reach to this point. At the end, we should start from the beginning. Otherwise, this program runs just once, and then when we reach to the end, if the program is at this point and then remain at this point, let's say at the last rung, remain here, then if there are any change in the variables here on the process, on the plan, set point change, temperature change, the PLC cannot understand that. Otherwise, it will start to run the program again from the beginning. Again from the beginning. So, in fact, the program in the PLC run in a cycle. It runs the program from the beginning, goes to the end one by one, and then again starts from the beginning, goes to the end. And then from the beginning, goes to the end. But in addition to having this cycle and running the program that we built that on the PLC, on that OB1, main OB15, there are some other programs some other tasks that must be also run or executed in each cycle. 2 important ones are reading from the input and sending the data to the output. You remember that I mentioned that the input card for any input card, okay, any input card which is connected to the sensor, let's say to the, for example, to the switch, 24 volt, the input card sends that voltage, 0 volt or 24 volt, for example, or 0 volt, and according to that, change one specific bit in the memory. Change the state of that specific bit. For example, 0 to 1, 1 to 0. Change that or assign, let's say, assign the value 0 or 1 to that for digital input, or assign a value to an analog. For if it is an analog input, assign the value to a memory board in the memory. But this, and we have lots of inputs, but this reading does not happen, let's say, continuously. It does not happen continuously. It happens only once in each cycle. So only once in each cycle. So, for example, if this is our program from the beginning to the end, this is the program that we built, for example, okay, This is the program, our program, I don't know, some timer, for example, like this, okay? So before starting the program, and the PLC starts the running the program or executing the instructions one by one from top to the end, before starting that in each cycle, PLC read the inputs, all the input, check the input cards, according to the voltage here, read the data and assign the value in that input image memory. And during running the program, when we said that input 1.0, for example, PLC does not read that from the input card. It just reads that from the memory. And this memory has been updated at this time, not during running the program. This is important. Why? For example, let's assume that you have a program that somewhere here you use input 10 for some reason, okay, for assigning something. And then you have a very long program, and then somewhere else also, again, you use that input 10 to, for example, activate a timer, for example. When we build this program, something that we expect is that the state of the input 10 here and here are the same. We expect that they are the same. This input 0, if it is 0 at this point, if it is true here, or it is true also here. If it is false at this wrong in this part of the program, it should be false also in here. But if the PLC read the input 10 directly from the input card, if it read that directly from the input card, and then what will happen if it just maybe take just 2 milliseconds, 200 milliseconds, not too long, 200 milliseconds, 20 milliseconds, or even 2 milliseconds. It's very fast, but it takes some time. What will happen if sometimes between these two, between running this part and running this part of the program, the state of this input changes. For example, at the beginning, when the program was at this stage, at this rung, or at this line, the input was 0. And then after, I don't know, 5 milliseconds, after 100 milliseconds, the input changed to 1. Because somebody changed this, pushed the switch. And then the state of that here is different from this one. And this is not something that we expect when we write the program. Something that we expect is that the state of the input everywhere in our program is the same. The value is exactly the same. To implement this, PLC does not read the input in the program directly from the input card. It reads that from the memory, and this memory does not update continuously. It just updates once in every cycle. So if the input here, if this input was 0 at this point, it reads that, and input 10 is 0, for example, 10 is equal to 0 at this point. This is 0 all through the program. And nothing changed, so all of them read that to be 0. Nothing will change in the inputs 10 until again it returns to this part. And again read that. Maybe that changes, becomes 1. Okay, this will be 1, and for all of the runs, all through the program, it is equal to 1. So this is the reason that the PLC read the input just once in every cycle. Similarly for the output. The output does not, if we have this here Q.3, 2.3, for example, so the command is going to the output 2.3 is going to be, I don't know, 1, for example, at this point. This value does not send to the output PLC card. It saves in some output memory image. It's called output image memory. It saves there, And this value send or write will be written on the output card at the end of the program, not when it is generated. At the end. So this is the structure. The program at the beginning, all the inputs read and the data saves in somewhere that it's called input image memory. During running and nowhere else, the input does not change anymore, all through this one cycle. Then the program runs, okay, and the outputs are generated, but these generated outputs are just saved in the memory. And the memory is do nothing, and the PLC do nothing with that memory, just save the values on that. Then at this point, all these memories will be sent to the output card. So update the output card according to the memory, output image memory. There are also some diagnosis. For example, it should check also to be sure that the battery of the CPU, the CPU generally they have a battery to keep the program, even when there's not any power connected to that, or some others regarding the clock pulse, or even the speed of this cycle. You can change the speed of this cycle. It's possible. It cannot be less than some value, depending on that program, but you can, for example, your program needs just 100 milliseconds to be executed, all the program. And you need also, for example, I don't know, 1 millisecond to do this, okay? So the scan time, one cycle cannot be less than 101 millisecond, but it can be more than that. You can select that. So all of those there are some diagnoses and or communicating with other PLCs, send information to the other PLCs, not to the output card, not reading from the input card, but send the data through the field bus to the other PLCs, to the HMI, communication with the HMI, send the information to the HMI, or read the data or the commands from the HMI. All of them, these are something that we do not write that. We use them, we use that HMI variable, but the PLC hardware, let's say the PLC itself and the HMI must communicate. All of them are done here. So we call this a scan or a cycle. PLC cycle scan or PLC cycle or PLC scan is the name of that. And this is the structure. Depend on the PLC, all of them has this structure, this general structure, but depend on the PLC brand. Some of them, after executing the program, first update the output and then do the diagnosis and communication. Some of them first do the diagnosis and communication and then update the output. This depends on the PLC. It's not something important. In this, for example, here you see that the input, read the input, run the program, do the diagnosis communication, and then send the output to the output cards. In this one, you can see this is the execution program, okay? Logic program. First, scan the input, read the input, do the programming, then update the output, start the new scan, scan, and then do internal check, so diagnosis. This is the diagnosis. So you see that after running the program, first update the output and then do the diagnosis, and then go to the input in this one. But in the other one, it is they are changed. So it is not that important. Something that is important first, it is that it is a cycle. It is a cycle or a scan. Two, the second important is these two, that the input and output, and also this one, that we have these three in addition to this one. We only write the program of this part. We do not write any program for these. These are something that take care by the PLC operating systems. But these are also part of the program. Okay, this is the first issue. Any question? Okay, let me just mention that, let me just increase the time for the quiz. We need a few more minutes to finish the quiz, to this part, and then start the quiz. So let me just add, I don't know, what about Okay, to be sure that we have enough time, I changed the time to 11, but we will change that at the end when the lecture finished. Okay, when the lecture finishes, this is of course Canadian time, but for you it is 6:30, but this 6:30 is just done. I will change that again when we finish this part of the lecture, and then, okay. Okay. The second issue is regarding the PLC language, programming language. The language that we studied was ladder diagram, or LD or LAD. In fact, the IEC has defined 5 programming languages based on this standard. This is a standard on the IEC, that there are 5 programming languages. Some of the PLCs, all of the PLCs support this ladder diagram. All of them has this ladder diagram. Of course, the detail on the format might not be exactly the same. For example, the timer format, the comparator format, the counter format in the Siemens PLC and the Allen Bradley PLC and the, I don't know, Omron PLC and like that. They are not exactly the same. They are different, but all of them support. So the ladder diagram supported by all of the PLCs. Most of the PLCs support some of the advanced programming language, some other, let me say other programming language, not necessarily advanced, other programming languages. And some PLCs, advanced PLCs support all of them. We are not going to go through the detail on these 4 other programming language, but just have a look to them to at least recognize, okay, this is the, for example, FBD, function block diagram. This is SFC. Just to know that, okay, these are other programs. So we are not going to go through the detail on that. Let's start from it. This is the circuit diagram, the electric circuit diagram, okay, control system, hardware control system. Ladder diagram language is this. That we have already studied, which is very similar to this. It's this ladder is graphic language. Yeah. Any question?
Are we seeing the same screen?
Oh, you see just the same screen. Nothing changed? Nothing changed?
I'm reading 2 PLC programming languages. Yeah, now I can see the diagram.
Oh, now you can see that PLC programming language. Can you see?
Yes. Yes.
So could you see this PowerPoint? That the title of that is PLC programming language. Can you see? Oh.
Binary logic operation.
Binary? Binary logic operations. Yeah, that's correct. Yeah, exactly. Okay, that's good. So you can see.
Okay.
So this is the ladder that we have already studied. The detail, we're not going to go through the detail on that. The other one is function block. Function block is very similar to the logic that we use in the logic language. So, and this input and send the output to that. It is very similar to this one. Let me show that by this. It's very similar to this one that we use in the logic circuit or in the so for example, A and B is C, or A or B is C. So instead of this structure for and or, this series or parallel connection to implement and or, it's based on the just graphic symbol for them. But instead of, some PLCs use these graphic, well-known graphic symbols that we use in logic circuits, or they use this simple structure. for and or. So it is based on, it's a function block diagram, very similar to the logic. The next one is a statement list. The statement list, okay, or instruction list, is very similar. It's a text-based, let's say, programming. It's not assembly, but very similar to assembly. Or let's say, let me say, it looks like an assembly language, but it is not assembly. It's not assembly. It's not assembly, but very looks like an assembly. So and that would input 1 and save the data on output 8.0 or output 8.1. So it's very similar to the assembly. If you are familiar with the assembly language, this is very similar to that. I'm not going to go into the detail, but this is a structure of that. The next one is sequential flowchart. Sequential function chart. Sequential function chart is very similar to the flowchart, if you're familiar with that. So it based on on the sequence of some programs. For example, this is a very simple program. This is the initial state. When we are in this initial state, then this transition will be checked. If this is true, then the state changes to this one. When we are here, the transition check. If the transition is correct, then we move to the second, to the next state. In each state, we have some program. For example, here, let's read that. We are in the initial state. Then it checks if the motor is off and the starting signal is on. It means that the starting, somebody pushed the start signal, is pushed to turn on the motor, and the motor is off. Then the program, some part of the program is run to start the motor. And then if the motor is on and somebody pushes stop, then the part of the program to stop the program, the motor runs. So it's very similar to the chart. And finally, structured control language. Structured control language is a high-level programming language. It's something like C, VHDL, C#, or something like that. It's a high-level programming. So it's a text-based. And so, for example, if you're going to implement this one, we are not going to go to the detail how to do that, but just very short look at that. Okay, this logic, or this one and this one. So here you see that the motor is equal to the motor. This is motor, and this is motor. Okay, so start or motor multiply by the stop. So this part is implemented by this formula. So again, I'm not going to go to the detail, and I don't expect that you understand how to do this programming. Just to look at that, it's based on the high-level programming language. If you are familiar with any high-level language like C, I don't know, Python, Java, MATLAB, Fortran, BASIC, or any of them, you can see that it's something like a high-level programming language. So according to the IEC standard, there could be five programming languages in the PLCs. This latter programming language is the base and supported by all PLCs. There are some programming languages that might be supported by the PLC, by some PLCs. So you should take care of that. Maybe the program that you see, for example, you go to the industry and then you open the program and you see that, oh, it's not ladder diagram. What's that? Maybe it is based on statement list. Maybe it is based on sequential flowchart. Those PLCs that support these programming languages might give some conversion, let you to convert that to ladder or ladder to statement list, but it is not something that can happen all the times. The program that we studied was ladder diagram. Okay. The third part is the program structure. The program that we built, all the program that we build for our control system, we build them under this main or OB1. But you can, this is called linear programming. So all the program is in the same file, somewhere at the same, let's say, position. All of them are in organization block number 1. This OB1 is called organization block number 1. But you can divide your program to some part and save that to some subroutines. So let's say some other files and just call that. So you can make a kind of structure programming. So instead of having all the programs in the same line, for small programs like the ones that we have, it's, I don't know, 10, 20 or something like that, number of the rungs or lines. That's linear programming. Everything in the OB1 is good. But just imagine for a machine, for example, I remember that I worked with many years ago with a machine to build the crankshaft in the cars. And the program was more than 10,000 lines. 10,000 lines in the same file. It was very difficult to understand that. The program was ready. And we're supposed to commission the machine. And it was very difficult to understand the program because it was 10,000, more than 10,000 line program, all in the same file. It was very complex to read that. But you can divide your program to some subroutine and just call them. For example, instead of having the whole program for, I don't know, temperature control in the main OB1, you can call the temperature control of the heater, and that temperature control program is somewhere else. So when you read the main program, you don't need to go through all the detail. You just read, okay, here, control the temperature. That's good. So here I will. What's the detail on that? Maybe you just skip at this point. And later, you read that and check that. So have a structured programming. This is very important for larger scale plants. I don't want to say very larger scale. As I mentioned, that machine was just a machine to build to make crankshafts. It was not a large. It was just in the size of a room, a small room, not a large room. It was in the size of a room, so it was not a very large system, but the program was more than 10,000 rounds, 10,000 lines. And so for a plant like power plants, like a thermal power plants, the number of the lines of the program, I don't know, but it should be in the order of more than 5,000, even 10,000 line. More than 50,000 or maybe 100,000 of lines. It's not possible to write all of them in the same file. And then if you do that, if we made a mistake, it's very difficult to find out where. So it's better to divide that to subroutines. Depend on the PLC, how to divide that, the PLC brand, how to divide that depend on the PLC. In the Siemens PLC, in fact, it divided to blocks. There are three blocks or three type of blocks in the Siemens PLC. Organization block, function block, and function. This is a little bit confusing. This FB is function block, but FC is simply function. In old version of PLC, Siemens PLC, now we use S7, but up to S5, it was called program block. I don't know why they changed that to function. I don't know. But up to S5, it was called function block. instead of program block instead of function. But no, now it is called function, and it is a little bit confusing, the difference between FP and FC, because both of them are function. But anyway, you can divide your program into three different blocks. You can divide that to different blocks, and these blocks could be organization block, function. What's the difference between them? First, organization blocks are the blocks that we do not call them. We cannot call them. The organization blocks called by the PLC automatically. For example, this is scanning that I mentioned here for reading the input, doing the executed program, and for example, updating the output. Execution program is in OB1. I don't remember the OB number, but there are some other OB organization block to read the input that the program inside that organization block with some number. I don't remember what's the number. And this one also. So when this organization block runs, the program read the inputs from the card and save them to the memory. Or when this organization block calls, the program read the output memory and write them on the output device, output cards. These organization blocks we cannot call them. They are called by the operating system automatically. Some of them we cannot even change the program. For example, we cannot change any program in this OB1 to read the inputs or read the, update the outputs. But for some of the OBs, we can change them. For example, there's an OB, again, I don't remember because the numbers, there are many OBs. One of the OBs calls if the battery, the voltage, let's say, charge on the battery, the backup battery is low. There's an OB that is called. We can program that. So say, okay, what to do if the battery charge is low? By default, do nothing. Just a lamp turn on the PLC. There's a lamp in the PLC CPU card that just turns on to indicate that the battery is low. But maybe it is important for us to be sure that the battery, if the battery is low, for example, back up the information. We want to back up all the information, so we can change the program. So for the OB, we cannot call them, but for some of the OBs, we can change the program. For some of the OBs, we cannot even change the program. The program is there. So these are organization blocks. The main organization block is OB1. The OB1, also we do not call OB1. The program called that during the scan time, in somewhere during the programming cycle. But we can change the program. The program is there. Function blocks is something that we can call and function also. We can not only call them, but also we can change the program. What is the difference between them? Function block, when we call a function block, the variable here, the variable that are in the program are not global variable. They are local variable. So they are kind of indexing program. What they mean? Okay, let's assume that you have a function block that is the program. Let's imagine this. You have a power plant that, for example, you have 100 motors, AC motors, simple AC motors, that let's say they might be run clockwise or counterclockwise. So you want to change the direction of them, clockwise or counterclockwise, turning them clockwise or counterclockwise. That's a program. Okay, there's a program, something in the order of, I can say, 10, 12 lines of program to control this. All of those 100 AC motors that are going to be run either clockwise or counterclockwise, the program of them are exactly the same from the structure. But something that is different is the input and output of them. For example, the output command for this motor is Q0.1. For the other motor is Q, I don't know, 5.4, for example. For the another motor is Q, I don't know, 6.1. So the structure of the program is the same, but the variables are not the same. This is something that we don't need to write 100 times that program, because the structure of the program is exactly the same. Nothing changed. The program is the same. Or for example, a PID, a PID controller. The structure of the PID controller is the same. The only thing that changed is the parameters of PID and the input to that and the output out of that. So the program, the structure of the program is the same, only the variables are not the same. This is something that can be implemented by function block. In the function block, when we have a function block, we write that program, for example, for the clockwise, counterclockwise control of the AC motor. We build the program, but the variables are index variable. Every time that we call that function block, and then we can call for 100 times, we call them 100 times. For each of the motors, or each of those 100 motors that has the same program, we just call that file, that function block. And for each motor, when we call this function block, we also give it the variable numbers. For example, if this is the motor number 1, when we call that function block, we say that we give that this information to the function block that the output is Q10. If this function block is called for motor number 2 and the output for motor number 2 is Q, I don't know, 5.4, then when we call that function block, when we call this function block, we give Q5.4 as the output variable address. So it is indexing addressing. So we call that the program and also define the program. How to do that is something that I'm not going to go through that. It's based on data block and the Siemens PLC, and we are not going to go through that, but just to know that, okay, this is the structure. But in comparison to that, for the function, the variables are not in the indexing, or let's say the variables are global. So we cannot change them. We cannot change the variable address in the functions. They are constant. I don't want to, they are not, it's not, those variables are constant, or those variables, we cannot change those variable address. I mean that the address of the input, the address of the output, the address of the beat, the address of the timer, we cannot change them. It is just to make the OB just structured. So it looks like this. You copy part of the, or let's say cut part of the program in the OB, okay, part of the program, and save that in FC, just to make the OB, and then here you call this FC. It's just to help increase the readability of the program. Instead of having all these runs here, just call this FC, and this FC looks like it is part of this. But for FB, when we call that, we also give the data, the address of the data, of the input, the address of the output, the address of the timer, the address of all of this. Okay, so it's possible to change them. And finally, regarding the hardware connection of the sensors and the output devices to the PLC, let's look at these two and then look at it. Here you can see that the sensor, for example, the power supply outside of the PLC, this can be a sensor or can be just a switch, for example, is the power, positive terminal is connected to the sensor and the other terminal of the sensor is connected to the PLC. But this one and the ground of the power supply is connected to the common terminal of the PLC card. But in this one, the PLC, it is the negative terminal of the power supply that is connected to the device, and the device is connected to the PLC. And this is the positive terminal of the power supply that is common. The difference is that in this case, the direction of the electric current is toward PLC input. Here, the direction of the current is out of the, from the input card, not to the input card. This is called sinking input module. It sinks the current, let's say. And this is sourcing input module. It's a source. It looks from the sensor point of view, From the sensor point of view, in this card, the PLC is the source of the current, because the current is from the PLC to the sensor. But this is from the sensor to the PLC, so it sinks the input current. Some of the PLC cards are sinking, some of them are sourcing. Are there any benefit on them? Nothing special, and if there are some differences, not important for us. The only thing that is important is that when you are going to select an input card, or when you work with the PLC and you're going to wire the sensor to that, take care of that, whether it is sinking input or sourcing input, because the direction of the connection of the supply is different. In the PLC that we have in the amateur trainer, it is a sinking input. So the positive, 24-volt positive, is connected to the switch, and the switch connected to the input. And the negative is, these wiring are ready for your amateur trainer. But please take care of that. When you are in the industry, you should take care of this. Don't make a mistake. The direction, if you make mistake, the PLC card might be gone. Similarly for the output. In this type, the output of the PLC is connected to the device, for example, the relay contactor, and the other terminal of the relay is grounded. Of course, we need also to connect the positive terminal of the supply to the common. But there are some other cards. This is the structure that we have in that PLC 1200 in the amateur trainer. And I also have the same in the Humber. But there are other output cards that, in fact, it is the positive terminal of the power supply that is connected to the relay, and the other terminal of the relay connected to the PLC. And the negative terminal of the power supply is connected to the COM terminal of the output cards. This also, if you look at this from this device point of view, this is the source of, this is the current direction. So the PLC output card is a source of current somehow. But if in this case, the direction of the current is from the device to the PLC. So the PLC, in fact, sinks the current. So it is a sinking output module. This is sourcing. Again, it is very important to take care of that. Whether the PLC card is sinking, output card sinking, sourcing or sinking. If you made mistake, we may make a wrong connection, and it is possible, sometimes happen, that the PLC card goes gone, or maybe just that terminal. That terminal cannot be used if you made a mistake. So this is important to take care of that. Again, I'm not going to go through detail on that. There are some detail you can study later by yourself or like that. Just to know that the direction of connection of the devices to the PLC input and PLC output card depends on the type of the card. So we should take care of that. We should check that, and according to that, properly connect that. Okay, so that's all. This was the last slide for this lecture. So any question, if you have any question, let me. Otherwise, I open the quiz for you. Any question?
Yes, I have a question.
Yeah, go ahead.
And it's not concerning the slides that you've given us, the complement ones. Do we have an email for Humber College?
A general email?
No, when I wanted to download something, the resources that you've given us, it required that I provide that email.
Yeah. Regarding that, I should check with Jorge if they are going to give you an email from the Humber or not, but you can use your own email, any email. It's not important. You can use your, I don't know, for example, Sigalagala email, your own email in the Sigalagala. There shouldn't be any difficulty to have, or your personal email even. But whether the Humber will provide you an Humber email, it's something we should check with the Jorge. I will check him. I will ask him, and I don't know. I don't know what's the policy. What's the policy of the college? Whether they give the Humber email to trainers or not? I don't know. I will check with Jorge. But regarding that Siemens program, the email address is not important to be from where. It can be from Zigalagala, it can be your personal email like Google or I don't know, Gmail or Yahoo email, or yeah, so you can use any email number account that you have. But I will check with Jorge. If it is possible, I will tell you.
Yeah, I tried using my own my personal email, but it's not. I am not able to download.
Oh.
Can I share my screen?
Let's not now, but let's check that together another time, because I prefer to start the quiz and then we can have an appointment, okay, together. Then you share a screen and show me the steps to check what's wrong, okay?
Okay.
Okay, namaste. So please send me an email regarding that to set an appointment together and check what's the problem.
All right.
Okay. That's good. Any other question? Yep.
No, it's just a comment.
Yep. Go ahead.
We managed to download the PLC sim TIA today finally. So hopefully from tomorrow we can be able to do the assignments and following week.
Very good, because yesterday I checked the assignments. Unfortunately, I noticed that nobody has yet submitted. So you download that. Very good. And which email did you use? Your institute email or your personal email?
My personal email. I had to open an email and then access the TIA Siemens portal. I registered and did everything. It had a challenge. I had to use somebody else's machine, and we hope from tomorrow we may be accessing his computer so that we can learn.
Very good. Good news. Thank you to let me know. Very good. Okay, I will extend. Don't worry about that. I will extend, but of course I should check with the Jorge, because there's some deadline for the end of the program. I cannot pass that. I will check with Jorge that to see what's the final time that we have, and according to that, I will extend the time. Don't worry. Work on that and start and submit your report. Okay, very good. So let me enable the quiz. again. There's just 3 questions, and you have 15 minutes to answer that. So I set that from now, 11 o'clock in here, or 6 o'clock over there. And you have time, 15 minutes to work on that. Okay. So it is open for 15 minutes and yeah, 15 minutes to answer that. So could you please check if you can start the quiz now? Okay, I hope, I assume that everybody could log in, start. If there is anybody that could not yet and have any difficulty, please let me know. Otherwise, I will stop this session in 1 or 2 minutes.
Please, I'm not able to access the questions.
You cannot?
I'm not able to see the questions.
Well, the quiz is under lecture 8. Under lecture 8, at the bottom, there's quiz number 2. Do you see this quiz number 2?
Let me just go and check.
Yeah, go to the lecture number 8 at the end of lecture number 8. Okay, Vincent, could you?
Not really, not really.
Could you see that? Can you see that? If not, please refresh. Please first refresh.
I'm able to see, but it's not opening.
It's not open?
Yeah.
Are there anybody else that has this problem? Not possible to open? Let me check again the time.
Let me check now.
Okay.
Okay, now. Okay, now okay.
Oh, no, okay. Okay, very good. So continue.
Okay.
Good. Okay, very good. So I assume that everybody has successfully started. I'm going to stop this session.
Okay.
Okay, so I'm going to stop this session if there's not, if everybody has already. Okay, goodbye. And yeah, I will send an announcement regarding the final exam later. Goodbye.